In this video, I'm going to use a data set out of the wooldridge package to just illustrate some regression models. So this is going to be the first of a few videos where I use data sets from this package to illustrate some models that we can look at. So what I want us to do first is to be in R Studio, and we're going to have a new R script. You can see that I have one right here. And I just want to point out that if you have not installed the wooldridge packages, you can do it with the install packages wooldridge command. So let's run it real quick. We'll just highlight run. Let's cancel this. Actually, you can see I actually loaded it already in my packages. So I don't need to install it again, but if you haven't, you will need this line of code, and this line of code installs the wooldridge data set repository. So okay, we've installed it. We can get kind of a glimpse as what's in the repository with the data command. So if I type in data, you can just kind of scroll through and see all of the 111 data sets that are located in the wooldridge package. And we're going to be looking at the wage 1 data set for the problem set, but we're going to look at the CEO salary 2 data set today. So I want to type that in here, data CEO sal 2. Just click on that. We're going to delete it from the console because I'm going to run it out of the R script. So I run it, it is loaded in. You can see the data loads lazily, so we're going to double click on that. You can see what the data set has. It's 177 observations of 15 variables. So in the data set, this data set contains CEO data for 177 CEOs. Okay. So in this data set, and you can view the data set with the view command. So the view CEO sal2 views the data set. So I always recommend looking at the data set before viewing it, or before estimating a regression model. Okay, so let's say that we've had the data set. You can see the salary of the CEO, and I believe this is in millions. The age, whether or not the CEO went to college, whether or not they graduated from college. You can see the amount of company tenure, that's COMTEN. You can see the CEO tenure, how long have they been a CEO. You get the sales, the profits, the market value, and then you have some logs of these values. You've got squared company tenure experience, CEO tenure experience. You've got a profit margin. So you have a couple of variables that are interesting dependent variables based on CEO characteristics. So profit margin as a function of CEO characteristics might be interesting. So let's just look at exploring a few different regression models. The first one we're going to do, let's just call it sales reg 1, and we'll use the linear model, the LM command, to estimate the sales as a function of CEO salary. So sales as salary, and we're going to tell R to use the data CEO sal2. Note that I could put CEO sal2 $ sales, and then I wouldn't need that data command anyway at the end. So this estimates sales as a function of salary. And sometimes I think it may be useful to write down the regression model that's being estimated here. So we should say something like we are estimating sales equal B0 plus B1 times salary plus E. And the error term is the residual. Okay, so this is in levels. So salary is measured in dollars. So beta 1 is going to be extremely small relative to what it would be if we looked at a log model. So let's run this model here. You can see it showing up in the data environment. Okay, now maybe we want to summarize the model to learn about it. So let's type in summary of sales reg 1 and run that. Okay, so in the summary, we have called sales as a function of salary. The data is CEO salary 2. And you can see the residuals range from minus 18,596 to 43,219. The model that we estimated, and you can see right here, is that I'll type it in here. Sales equal 118.03 plus 3.9399 salary. And we can interpret the model as being significant in that we reject the null that B1 equals 0. The t-stat is 5.44 with p-value 1.79 times 10 to the minus 7. R tells you down here with the 3 stars that we would reject the null at the 99.99% level. R squared, so in this model, the R squared is 0.1397 adjusted. Okay, so now we could plot these data. We could plot CEO sal to $ sales, CEO sal to $ salary. I could plot these here, and you can see that most of the data are clustered within particular range. Actually, it would have been smarter for me to plot salary and then sales. So let's do that instead to be consistent with XY. We change it here. Okay, you can see that the data are clustered kind of in this lower quadrant of the graph, but you do have some outliers. So the data are skew right in both directions. And so a natural fix to this might be a log model. Now, we could add this regression line that we have right here could be added into the graph. And we do that with the AB line formula. I type in CEO I type in LM. So I'm going to re-estimate the model. We're just going to put this in here. Let's copy it down here. And we'll run it. You can see the regression line that we estimated here is actually added into the graph down there. Okay, and so the scaling is so kind of poor that you have a difficult time even seeing the intercept of 118.03, and that's a potential issue with interpreting this model. So this is a simple model where sales are a function of salary. Now we interpret the coefficient beta 1 as a $1 increase in salary yields $3.93.99 in sales. So that is how we interpret that slope. Now we could go ahead and estimate a different regression model. Let's call it sales reg 2. We're going to estimate the same thing, but we go back and we just have log sales let me make sure I have a CEO sal to log sales as a function of log salary. We don't need the data here because the data has been referred to already. So I run this, I'm going to summarize it as well. And what you should note is that the regression significance levels and our squares should be very similar, but the coefficients are going to change a bit. So we run that. You can see we have it here. You can take a look at the coefficient on log salary as a function, or log sales as a function of log salary, and you can see that it's still significant. We are still estimating sales as a function of salary, but instead of estimating the unit value, we estimate log sales. And what we estimated here was that log sales is equal to B0 plus B1 log salary plus an error term. And in particular, the model that we estimated is the intercept is minus 1.0125. The slope is 1.2523. And so when we have a log specification, we interpret the coefficient as a 1% change in log salary would yield a 1.25% change in log sales. So beta 1 changes to a percent interpretation. A 1% change in X yields a 1.2523% change in Y. So instead of when log salary goes up by a unit, we're thinking of it as it being interpreted in the percent. Rather than salary going up by a unit, we think of it as a unit change. Salary may not be the only thing that explains sales. So if we go back to this data set, there are some other variables associated with the CEO. We can include as many of them as we want in the model. I do want to just point out before we do that the plot changes when we call it log salary and log sales. Let's just copy that down here. Just put an L in front. There's the L in front of all of it. Let's run it. What I want you to see once I run it is that the data are going to look a lot more, you're going to see a lot less skew in the data. And in fact, you can see the regression line, that slope is pretty evident. You can see this is a 1 unit change in log salary, and it's about a 1.25 unit change in X. So you can see that we're going to go through it about minus 1.0125. Note that as I go through the code, I comment the interesting features of the regression model, and I also delineate what I'm doing. So it's really important when you estimate a regression model to, I think, write down the regression model that you're estimating as a comment, and then summarize a little bit of the results in the code so people can potentially directly interpret your R script without having to run the code if they didn't want to. That's something that I like to do that other people may vary. Let's take a look at sales reg 3, okay? And we're gonna continue to estimate a linear model, but now we're gonna include not just salary measure, but also tenure measure, college measure, graduate measure, CEO tenure squared measures. We're going to include a bunch of different measures. So let's take a look at the log sales again, but we'll estimate it as a function of tenure plus tenure squared for both the company and the CEO. And then we'll still include log sales. We'll include a measure of whether he graduated from college, he or she. Okay, and we'll run this model. Let's take a look at what happened. We appear to have dropped a variable in the model, and let's try to take a look at why. Let's summarize sales reg 3. So we have tenure, square, graduate, and you can see the problem here. When I estimated the model, I have log sales as a function of log sales. So what we wanted to have here was salary instead. So the nice thing about running this right out of the our script is that we can just change it. Everything will change. We'll re-estimate it. We'll summarize it. And now you can see some things that start to matter as far as sales go. So sales still explained by the salary, but also you have something related to whether or not the individual was a college graduate, the tenure squared, the company tenure squared. So it's important to write down the model that we estimated here. So let's write it down. We estimated, we'll put a hashtag log sales equal B0 plus B1 company tenure plus B2 company tenure squared plus B3 CEO tenure plus B4 CEO tenure squared plus B5 log salary plus B6 graduate. So we have a model that allows for nonlinearity in two of the different x variables, and we have a log salary and we have a log graduate. So we're going to interpret all of the variables in percent terms of y, but we're going to interpret some of the x variables as unit changes in x. So when we go back to the summary, go back and look at the console here, you can see that we have a measure for tenure. This is a 1 additional year of tenure leads to a 6% increase in sales. That's a company tenure. 1 additional year of CEO tenure leads to an 8.54 decline in sales, although we do see some nonlinearities on both ends with the squared terms, but they are not significant. There's still a relationship between log salary and log sales. So the log salary variable didn't actually change that much by including these other variables. And the college graduate variable, by going from 0, you didn't graduate, to 1, you did graduate, there's a 37.6% increase in sales. And interpreting that is something that we need to be able to do. So for this model, what we can say is that all the x variables, instead of, except salary, are unit changes, but the response in y is a percent change. So a unit change in x is leading to a percent change in y for everything, but salary, which is also, now we're looking at a percent change in x, is a percent change in y. So with this data set, we have estimated sales as a function of salary, log sales as a function of salary, and then log sales as a function of a bunch of other things in the data set. One thing that we could do instead is maybe estimate a profit margin regression. Profit margin was a variable in the data set. We keep all of these things that mattered for sales, but now sales also influences profit margin. So we have profit margin, and that's here, and we include a variable for sales as well. We can run that, explore a different dependent variable. You can see here that we'll just summarize that down here. And after looking at the profit margin variable, you can see that actually none of the variables in the data set seem to explain profit margin very well. In fact, all of these are insignificant. So while CEO experience, CEO, or while company tenure and CEO salary seem to make a difference for sales, none of these variables seem to affect profit margin, at least not in this data set. What if we were to change it to a profit regression instead of looking at profit margins, which may not matter as much if you have large volume? What if we look at profit instead? And I think this is where having some business knowledge would be helpful in dictating which regressions to estimate. So profit margin is a good thing, but it does not substitute for profits. Let's call it the profit regression. So profit margin versus profit, those are two different things. We'll run this. Run it again. Let's summarize it. You see again that the dictating factor here, now log sales matters a lot. So none of the, interestingly enough, very few of these salary or CEO measures have much of an impact, with the slight difference of salary. Salary matters a little bit. Now, if you take a look at the F-stat of this regression, the F-stat is testing the hypothesis of whether the coefficients are jointly significant. And the F-stat is indicating that they are. The p-value is much smaller than 0.01. You can see much of this is being driven by sales, more profit, but there is a little bit of additional explanation from the salary variable. So if we went back through and to kind of tease out whether the salary is really impactful, if we went through and excluded it from the regression, so let's just take out the CEO salary, let's include the other things that we had previously, call this profit reg 1, let's run it, and then we summarize it. We can take a look at the R squared potentially to see if there is much of an impact. R squared, very, very similar between models. Went down a little bit. Okay, so sales still driving the train here relative to the other variables. So this is a data set of CEOs' salaries measured against some key profitability metrics for a business. And in this data set, you can explore different specifications in R. So just a comment about how we're using R with this data set. We call the data set with the data function. We use the LM function to estimate the regression model, and we interpret the regression model. Here are the slopes that replace the unknown b's. These are our estimates. These test statistics test the hypothesis that the slope is equal to 0. And by slope, I mean the coefficients are equal to 0. So we should be careful about interpreting beta 1 as a slope because it's related to a nonlinear x variable. In our next set of videos, we'll examine another data set in R called airfare, where we can include what are called fixed effects. So let's actually load another data set into our data environment, and I'll do it in the R script. So we're going to load in a new data set, and let's just call data airfare. We'll run it. You can see it will show up in your environment as values, and you double click on it and it will load. You can see we have 4,600 observations of 14 variables. Taking a look at the data set, we have year, we have ID. This is a particular route. This is how long the route is. So if you have the distance and you have the ID, they are almost perfectly collinear. There are only going to be a couple of routes that are the exact same distance. This is the passengers on the route. Here is the fare. Here is the market share of the airline that flies the route. This is the distance. So the distance is in miles. This is the log of the distance. Here's a dummy variable for the year. Here is the fare, and here is the number of passengers and this concentration. So you can see that the concentration variable and the market share variable are actually the same. So we've loaded this data set into R, and what I want to estimate in this data set is the fare, the log fare, as a function of the market share, which is the percent of the market that a particular airline has, but I'm also going to include some root fixed effects here. Okay, so we're going to go back to our data set, and we're going to estimate an airfare regression. Call it airfare reg. And we're going to use the airfare data set. So we're going to use the LM. The data is going to be equal to airfare. And we'll estimate the log fare as a function of just the market share, B market share. just to make sure you get it right, you can often just type in with the $sign that market share. So how much do you charge is a function of how much of the market you control. We'll put a comma in between, run it. We'll also summarize it so we can see it show up in the console. You can see that as the market share goes up, log fare, interestingly, goes down in this model. But let's say we had some route-specific dynamics. So there's a possibility that some of this could be explained by idiosyncrasies in the route itself. Flying from Atlanta to Dothan is different than flying from Atlanta to Raleigh, even though they're relatively similar distances because of the competition. So we do this by adding in what's called a factor variable. The factor distinguishes a categorical variable value from another one. So when I have the factor ID, it's going to break apart the IDs into all of the different IDs that I have in the data set. So, when you go to this data point here, you've got ID 964. We're going to have a variable in for that particular route. And you can do this as long as you have more observations than factor values minus or factor values plus one variable for the intercept plus one variable for all of the other, plus one for each of the other variables that you're including in your model. So I can go back here, put this factor ID, I subtract 1, okay, for the last one. So I'm going to include a variable for each of the factors except for the last one, and I'm just going to use the data equal to the airfare. Okay, so we're going to run it, we're going to summarize it, and what you're going to see in the summary is that R is actually not going to produce coefficients for all of the different factors. It's only going to show you the first 200 or so. Okay, so let us open it. We'll run it. You can see that it's taking a bit because I'm asking R to produce 1,000 coefficients here. Okay. Let's say I want a summary of this regression. Summary airfare reg 1. Run it right in the console. It's taking a bit. You can see that it produced estimates for each of these different factors. But interestingly enough, once we included the factors in the model, the R squared went way up. Okay, it went from 0.05 to almost 100%. And the market share variable went from negative to positive. So these are what are called fixed effects. And I'll just summarize what a fixed effect is. We include put a hashtag by it here. We included a variable for each route with the factor ID variable. We subtracted 1 because if you're not in the first n minus 1 roots, you're in the last root. So basically, when you do this factor modeling, if you don't subtract 1, then you will have, it would be like including a variable for male and a variable for female and a variable for any type of other gender interpretation. Once you include the variable for the other, since if you're not male or female, you're in a different categorization, then you don't have the ability to estimate a slope anymore because the determinant associated with the matrix that you're trying to invert is 0. So this is something that we just have to watch out for. But what I want to highlight here is that this factor allows us to put a 1, 0 variable in for every category in our model. So this is something we should be thinking of doing. This is called a fixed effect. There is a route-specific effect on airfare, and we want to include that when describing how market share impacts fare, because if we don't include that, then we may get the impression that market share doesn't affect the fare at all, or it affects it in some type of counterintuitive way, when really the story is that the route is determining the fare. Okay, so we could have gone back to maybe look at this data set some more. We could include the distance measure, the passengers, etc., as other potential influences of the fare in addition to the fixed effects. So if you look at the number of observations here, you have about 4,600. If you look at the ID variable, if you scroll all the way to the end, you have 1,149 unique routes, and you have maybe 12 or 13 more variables that are of interest in the data set. You have plenty of degrees of freedom to test any of the hypotheses that you want in this data set. If you just wanted to include a couple of routes, you could do that, but you might be excluding useful pricing information. I want to show you one more thing that we can do with the data set, and let's go back to the CEO salary data set. So what I could do is create a variable for highly experienced CEOs. So if you've worked with the company for over 25 years, I could make a variable that describes that. And I could make a variable that describes whether you've been the CEO of the company for more than 10 years. I could interact the two to have like the most experienced CEOs in my data set. So I can create a variable, okay, and let's just call this CEO sal to experienced company. I define it if else is a test. So it functions like the if function in Excel, but what it's going to do is produce a column of ones and zeros for me, as I'll show you. So let's take a look at CEO sal to, let's just use company tenure above 25, then I put a 1 and a 0. And I could do the same thing with experienced CEO and just change that to, instead of company tenure, CEO greater than 10. Greater than 10. Then I can interact them, and I could make a new variable called CEO sal2 highly experienced, and just multiply the CEO Sal2 experienced company with the CEO Sal2 experienced CEO. So when I run this code, I'll generate 3 new variables. Okay, let's run it. You can see I went up from 15 to 18. Okay. And so now I have some measure of highly experienced CEOs. I could go back through and estimate, CEO, let's just call it CEO Reg 1, just mess around in the console a little bit. I could go back and estimate the profits as a function of highly experienced with the data equal to CEO Sal2, and then just summarize that. You can see that, based on this, there's very little indication that having a highly experienced CEO influences profits at all. So there are ways to sort of structure the data set in order to learn more about different components of the data set. We can break apart a categorical variable with fixed effects. We can use cutoffs to make binary variables that may be of more interest to us. So like you're focusing on particular parts of the distribution. These are all things that we can do to analyze the data further. So right here, what we did is we made a 1 or 0 variable that took the value 1 if the CEO worked for the company more than 25 years. And here we did the same thing, but we just asked if the CEO was CEO for more than 10 years. Then here we used a kind of a definition. We made an interaction term where we multiplied the 2 experience variables together. This added 3 variables to our data set. So these are just some things that you can use R to do some kind of basic analysis, things we can think to do, and we'll talk more about them in class.